Hey everyone, it's me, Allison again, and this is our second science and engineering chat, and we're going to be talking about black holes. I'm going to wait a little bit for everyone to show up, and today it's a little bit cloudy out, so the lighting is not quite as good. I've been playing with lighting like over the weekend, and I've got 4 different lights in here trying to get it brighter. um, but we will do what we can, and hopefully you can see everything. There's not too much glare. Yeah, there we go. All right, we got 6 people so far. Hey, Jersey. Jersey's watching. I also wanted to mention that I found out how to transfer my videos from Facebook to YouTube. And so I will be adding a YouTube link underneath of these videos in the discussion section so that you can go and review them on YouTube. I know some people don't have access to Facebook. So if you have friends who don't have access to Facebook, I will be posting them after the live on YouTube so they can go and watch them there. Hey Ash! And Amber's watching. Hey everybody! Okay, so I think we have enough people that I can get started now. As before, if you have any questions, you can go ahead and post them in the comments, and I will get to a question and answer session after the chat. So you'll get a chance to potentially have your question answered on the live. Okay, so everyone wanted to know about black holes. They're one of the most interesting phenomenon in the whole universe, and until very recently, we didn't know, we didn't have an exact idea of even how big most black holes got when a star formed a black hole. So first I want to kind of talk about what a black hole is, and that requires a review of what gravity is. Black holes are very, very tied into the concept of gravity. So everything has gravity, or anything that has a mass has a gravitational pull. And gravity is what causes things to drop towards the center of the Earth if you're on Earth. The further away you get from something like a planet or a moon, the further away from it you are, the less of an effect that planet or moon's gravity has on you. And so astronauts floating around in space don't experience as much gravity as we do on the ground. For black holes really, the reason that they pull things in, and the reason that they pull even light in and trap it so that it can't escape, is because it has so much mass concentrated in a small area that it has enough gravity to keep everything inside and won't let it escape. And if you have something that is close to the mass of a black hole, things will also find it very hard to escape. But the key thing with a black hole is that light itself cannot escape. And because we use light in order to tell time, and kind of, it gets weird. General relativity is weird, and it'll be a challenge to explain it on an elementary level. But because we use light to tell time, the time it takes for light to travel a certain distance gives us information. And so when you're inside of a black hole and light is not escaping, you can't tell time. Light stops, and so effectively time has stopped. And so that is a weird thing that you would encounter if, for example, you were an astronaut and you had the very unfortunate experience of falling into a black hole. First of all, it would seem to take a long time for you to like spiral in and get to this black hole, but once you pass the event horizon, effectively, and the event horizon is like the outside edge of a black hole, where it's the difference between you can still see the light and you can't see light anymore. As you cross that boundary, time effectively stops. So that is one weirdness about black holes that you don't get with stars and planets and other things that have mass. All right, so a black hole is a well of gravity where the gravitational pull is so high that even light cannot escape. Black holes show up as totally dark. You can't get any light signature from the black hole itself. You can get light from stuff around the black hole, but you can't get light from the black hole itself, so it shows up as totally dark in all wavelengths, X-rays, gamma rays, whatever. If you see those, it's from outside of the black hole. And they're formed after a massive star explodes. So black holes they're formed, and they have to have something that's very massive, like a star or a group of stars or galaxies, collapse inward and form that really, really, really tight collection of mass to form a black hole. All right, so I wanted to give you some history of black holes. Everyone kind of associates black holes with Einstein. Oh, my hand is blocking the mic. I apologize. Someone said it was better. I need to watch the comments while I'm doing this, which is going to be interesting. Thank you for telling me. It's over the mic again? I'm holding it by the side. Can you guys hear me? You can't hear anything. Okay, well that's interesting. Can you guys hear me if I'm holding it by the top of my phone? I knew there would be some sort of technical issues at some point. I'm good now. Okay. All right. So as I was saying, gravity plays a big part in how black holes work. And the gravity well is so strong that you can't even, light can't even escape from the black hole. So if there was some points in there that you didn't get, I will post a little bit of a transcript of the parts that you didn't get and give you more information later. Okay, so some history on black holes and their discovery. So there were theories, even as early as the 18th century, that some objects might have enough of a gravity field that they wouldn't allow light to escape. That was a theory from maybe the 18th century. John Mitchell and Pierre Simon Laplace came up with that theory. And then it wasn't until 1916 that the actual mathematical proof for black holes, a mathematical solution for that was found. Carl Schwarzschild, who you may or may not have heard of, the Schwarzschild radius of a black hole. He got some stuff named after him because he made important discoveries about the mathematics behind black holes. But we still didn't have evidence of black holes. No one had even found anything in space massive enough to become a black hole. And so it was more of like a theoretical thing. No one knew that these existed in nature. It might be some weird mathematical impossibility that only existed in theory. But in 1967, so this was a while afterwards, in 1967, Jocelyn Bell Burnell discovered pulsars. And these are a type of neutron star, which is slightly less massive than a black hole. They're not quite black holes. And no one had discovered anything this massive before. And so by discovering these pulsars, it kind of brought the idea into focus that maybe black holes were out there and we just didn't know about them. I forgot about this, but we hadn't actually had an image, a direct image of a black hole until April of 2019. I mean, the discovery was actually made earlier, a couple years earlier, but they didn't publish the first picture of a black hole until last year. The idea of black holes has been around since the 18th century. It took a while to get a picture, but I want to show you a picture of the black hole that they just, oops, it's not on I have an easel of awesome today. And so hopefully we can use that. But I have a picture on my little tablet here, and it's going to look less exciting than you think. It is very exciting if you're a physicist or an astrophysicist, but it looks kind of like a fuzzy donut. Oh, goodness. There we go. That's less reflections. That fuzzy donut is a black hole. The thing in the center is the black hole, and it's actually bending light around it. So you're seeing those bright areas are actually radio waves. It wasn't taken in optical. They had to take it in with radio waves. And so this is the first picture of an actual black hole in space. Before then, you could see, things that were results of black holes. You could see the results of things like light bending, which we'll get into. But this is the first picture of a real black hole, and it took a lot of effort to get it. It's located in the Messier 87 galaxy, so it's a black hole in a galaxy, and it was taken by the Event Horizon Telescope. So how do black holes form? We talked about what black holes are, and we mentioned that it's caused by the supernova of a star. But what kind of stars make black holes, and what is a supernova? So there are different sizes of stars. Our sun is a medium-sized star. It will not form a black hole. There are larger stars than our sun, and those, once you get up to about 2.5-ish masses, 2.5 times the mass of our sun, it can start forming a black hole. If it is smaller than that, it may form a neutron star. Those were the stars that were discovered by Jocelyn Burnell. And those are very massive and have a lot of energy coming out of them and can, collect matter and things like a black hole, but it doesn't have that light capturing aspect. Or if it's a small star, it might form a brown dwarf where it doesn't fuse anything anymore. It's not, the engine of the star has died. And so it just becomes this cold lump, basically. So supernovas. A supernova, if a star starts running out of fuel, stars are as hot as they are because of fusion. And it's usually things like hydrogen and helium that are fusing together and forming other elements. Once it runs out of those things like hydrogen and helium, it starts breaking down. It starts getting smaller and smaller and more compact. Once it gets to the point that it's so compact that even the atoms are squished together, it suddenly explodes. Most things on stellar timescales take like billions of years, millions of years millions is quick as far as outer space. But if you have a supernova explosion, I'm like so excited about this. If you have a supernova explosion, it only takes minutes for it to go from a condensed star to an exploded star. Minutes. That's crazy. Things are moving at relativistic speeds. It's a huge explosion. It destroys everything in the vicinity. And sometimes, after that explosion, it collapses back into a black hole. But only if it is a big enough star. And like I said, for a long time we didn't know how big a star had to be for it to form a black hole. Because things take billions and billions of years, it's hard for us to catch it in the act. There are supernova explosions that happen. The Swift telescope actually was one of the telescopes that was used to quickly catch a supernova explosion in the moment. But it takes time to like swing the telescope around. It's fast. It's a fast telescope, but it takes time to swing it around and point it at the supernova. So it catches the things that happen in the minutes after the supernova explosion. All right, in 2016, scientists were able to observe a neutron star merger using the LIGO it's not telescope, but the LIGO experiment. This measured gravity waves. So you remember I said that black holes depend heavily on gravity. All right, gravity has the ability to kind of ripple space. So if you have a piece of paper, I'm going to take my notes here. If you have a piece of paper and this is like, oh my gosh. If you have a piece of paper and you kind of bend it, it's kind of like if you had space, like imagine space as a membrane or like a little flat piece of something. You can bend it and it will warp space. So this is what gravity waves are doing. They're actually warping space. And they're very hard to detect because their influence is very tiny compared to some other things, such as machinery in your lab. You have to rule out the vibrations from the machinery in your lab that you're using to measure it from the actual gravity waves because they're very, very small. But they used gravity waves to determine that these two neutron stars were orbiting each other at a faster and faster rate until they finally collided and formed a black hole. So that kind of gave us more information on how black holes are formed. We actually saw through gravity waves a black hole being formed. All right, so I'm going to show you an activity that kind of demonstrates what I was trying to show you with the paper. I probably should have just gone straight into the activity. So I have, let's see if I can get this situated here. I have a t-shirt over a mixing bowl. I've got this mixing bowl here, and I've just put a t-shirt over top of it. Just like enveloped the mixing bowl with a t-shirt. All right, so I've got this flat. I'm going to try not to block the mic. There we go. We've got this flat membrane surface, and we're going to drop something with mass on it. So I've got something with a small amount of mass. Let's say you've got an asteroid or a moon, a small moon. All right, so we're going to put this on here, and it's not going to deform space-time very much. You can see that it's just a little bit of a dimple, maybe, but it's not deforming space-time very much. What happens if we put a big old heavy sun, or in this case a rock, onto our space-time here? Get my thumb out of the way. All right, we'll drop the rock. Oh my goodness, space-time has warped. So if you get something heavy enough, it would punch all the way through, and that's kind of what happens with a black hole. Or at least it gets deep enough, the gravity well gets deep enough that light can't escape. So this actually causes the bending of space-time. Now this is in 2 dimensions. Obviously space has 3 dimensions, and so it's... Oh, the video cut out briefly? Oh, okay, great. We'll just work with the technology we have. Yeah, so you can see if you put something in there, it's drawn down into this gravity well. So if I put something out here, it's going to fall into the gravitational pull of this object. Feel free to try this at home. Try different weights of things and see what causes things to fall in quickly and what things kind of like make it roll around a little bit but don't really draw it in. Okay, let's see what else I've got here. So the easel of awesome is actually for 6th through 12th grade. So if you are in 6th through 12th grade, please leave a comment here so that I know that there are 6th through 12th graders watching. I mean, I'll still go through it if you aren't, but I won't be as interactive. It'll just be me doing it on the paper up there. Okay. Oh, I had another picture of a black hole sucking the material off of a star in a binary system. So sometimes stars have kind of like, it's called a binary system, where there are 2 stars that orbit each other. And sometimes a star can orbit a black hole, or orbit with a black hole as well. And the black hole will start pulling material off of the sun. So the flattish looking blue one is the black hole in the middle there. And the bluish material around it is actually called an accretion disk. And an accretion disk is formed when material is pulled from other objects into a black hole. It orbits the black hole for a while before falling in. You can also see, because light doesn't always fall directly into a black hole, sometimes it like orbits around it, or sometimes if it's far enough out, the light just gets redirected. It'll come in, it'll encounter the black hole, it'll bend around that gravity well. Remember that sheet that was bent? So it'll come in around the edge and not fall into the gravity well, but it'll kind of get redirected around the gravity well. And that is one of the things that was looked at before we actually had a picture of a black hole. It's called gravitational lensing. And it doesn't just happen with black holes, it also happens with other massive things like galaxies and things like that. But, so you can see this ring around an object, and that ring is actually the stars and galaxies behind the object being the light from them before it hits our eyes being redirected around the object so we can actually see behind the black hole. Now this one might not have been a black hole, it might have been some other object between us and the object that is bent in a ring. But very massive objects can sometimes be found in the visual spectrum by looking at these rings that form from the light that has been warped around this very massive object. Oh, hey, 6th graders are here. Yay! That's awesome. Hi, Ginger. Okay, so we're going to start some question and answer time. Does anyone have any questions about black holes? And I'll go back through the comments real quick here, and I'll look for some questions. Let's see. Yeah, I'm sorry about my hand blocking the mic earlier. Like I said, I'll type in any information that you guys missed while it was being weird. No questions. Okay. Well, maybe you'll have some questions later. Maybe you can type it into the comments after the video is posted. So, oh, the one other thing that I wanted to mention is that black holes do come in different sizes, and you do have black holes that are formed from a star, or you can have black holes that form from a bunch of stars, or you can have these really big pieces. They're formed inside of these things called active galactic nuclei, and they also are formed in the middle of a lot of galaxies. Our own Milky Way galaxy has a big black hole in the middle of it. These are called supermassive black holes, and they are millions or billions of times bigger than a black hole that's formed by a single star. So we have kind of two sizes of black holes. We've got the stellar black holes, and they are smaller, a couple of solar radii, and then we have the supermassive black holes, which are millions or billions of times as big, and are usually formed in the middle of galaxies, including the middle of the Milky Way. Ooh, we got some questions here. Amanda asks, what happens if you fell into a black hole? So if you were an observer, and you were just in your spaceship at the edge of a black hole, and you accidentally got within the gravitational field of the black hole and your engines couldn't pull you back out, you would spiral the black hole for a long time in that accretion disk. And as you got closer and closer to the event horizon, the point at which light can't escape, time would slow down. You wouldn't notice because you would be inside of that dilation. It's called time dilation. But if people were watching from Earth and they were like, oh no, they're in their spaceship and they're gonna die, they would see you slow down as you entered the black hole. And once you got to the event horizon, time would seem from the people back on Earth to stop for you. So you would consistently be like falling into the black hole, and at some point light couldn't escape, and so they wouldn't be getting any more information about you. Sorry, I hit a button. Be back now? I'll wait a couple seconds here for it to be back. I'm gonna go ahead and answer another question. Clayton asks, is there anything that cannot get sucked into a black hole? No, as far as we know. Now, there are some really weird particles that don't have a mass. Things like neutrinos that I'm not certain whether or not they've actually determined if those can get sucked into a black hole. But anything that has mass or can be a particle, so like light can be both a particle and a wave, those types of things might not get sucked into black holes, but I would have to check that. There's some weird forms of particles that don't get affected by gravity as much, but I think they would probably still get affected by this amount of gravity. I just have to double check. Even black holes can get sucked into other black holes. It's called a black hole merger, and you can have one black hole get sucked into another black hole, and then they form a bigger black hole. It's just more mass, and so it just forms a bigger black hole. Amelia wants to know, how many black holes are there? There are a lot of black holes. There's billions in the universe. Some are small, some are big. But because there are billions of galaxies in the universe, and there's black holes in the middle of almost all galaxies, I mean, it's the majority of galaxies, there's probably billions and billions of black holes out there, and we don't observe all of them. How close can you get to a black hole? Well, it depends on the size of the black hole. If it's a supermassive black hole, it has a larger gravity field. I mean, gravity falls off as you get further away. But the more massive something is, the more it deforms space-time. So the more influence it has further from you. Like, yeah, for example, if you have something that's like an asteroid, the gravity is less than if you have something like the Earth. So that's why if you have a rocket taking off from Earth, it needs a lot more fuel than if you have a rocket taking off from an asteroid. It's easier to escape the gravity field of an asteroid. So it would be really hard to escape a black hole, but it would be, if it was a smaller black hole, it has less influence than a larger black hole at the same distance. Is there such thing as a white hole? I guess that would be if matter was being spit out of it. There's some mathematical proofs that predict wormholes. So it would be if you bent space-time so much that it actually, instead of just like wrinkling a little bit, it folded back over on itself. And so the two sides were touching. That would be called a wormhole. Now, we haven't actually discovered any wormholes, but it's a theoretical possibility. So maybe someday we'll discover wormholes and something will, come out of the wormhole on the other side. Not yet. Now, there are things called white dwarfs, which is a kind of star. So if you are thinking about white dwarfs, it's not a black hole, it's a dense star. Do black holes always combine when near each other, or do they ever repel each other like color magnets? So the magnets repel each other because of electromagnetics. The magnets actually have a magnetic field, which is a different kind of field than a gravity field. There's a magnetic force that's repelling those magnets. Gravity, as far as we know, doesn't have a repelling force. It only has an attractive force. And this is an interesting thing in physics, like that they're trying to figure out, because it doesn't have a pole. It's just a gravity well. So they don't ever repel each other. When two black holes get close enough, like in the binary star system that I showed you, it can be two binary black holes. And, oops, excuse me for a second. It can be two binary black holes, and those can orbit each other faster and faster until they fall into each other and form another black hole. They might also be in a stable system where they orbit each other for, billions of years, and they do just fine if they're going fast enough to, compensate for the gravity that's trying to pull them together. All right. Ginger also asks, can a black hole move? Does it ever go out like a star, or does it stay in the universe forever? Ooh, this is an exciting question that I forgot to mention. So black holes do evaporate eventually. If you stop feeding a black hole, if it stops eating, other stars and gaining mass, Stephen Hawking, an astrophysicist, actually came up with a theory that there's something called Hawking radiation, which involves particles at the event horizon, and it kind of emits a little bit of radiation, but it's really, really, really hard to detect because it's so small. And so we haven't detected it yet. But in theory, now we can't observe it because it takes so long, but in theory, black holes slowly dissolve over time. So if you had a really, really small black hole that didn't have much mass, it might dissolve over billions and billions and billions of years, but most black holes are dissolving so slowly that it would take them longer to dissolve completely than the entire universe has been in existence. So we probably won't observe that. But mathematically, in using thermodynamics, it is possible. All right, so I've reached the end of our questions. If you're in grades kindergarten through 5 and you want to just kind of end it here, I'm going to be going ahead with some calculations based on the physics of some of the things that we've described, and that's going to be for the 6th through 12th graders. If you want to stick around, that's fine. And, we got one more question. Could the universe be in a black hole? I don't know. I guess in theory, our universe could be inside of another universe, but I don't know. No one would know. Because you wouldn't be able to get any information out, right? Because you'd be inside of a black hole. All right. So, and William, I see your question. What if you get hit by a black hole as an astronaut? And we already answered that above. So if you go back and watch the live later, you can see that question as well. Okay, so middle and high schoolers, let's come over to my easel of awesome. And we're going to be going over some calculations for some of the things that I've already gone over. All right, let me know if you can't hear me. This is right side facing forward because I wrote backwards for you guys. It was surprisingly difficult, but this is all written backwards so that you guys can see it forwards. So this one, we're going to be calculating the center of mass of a binary star system. So when two stars are orbiting each other, they don't necessarily have exactly the same mass. So they may not both orbit at a point that is right smack dab in the middle of both stars. It'll be skewed towards the more massive star. So it's the same with black holes. Black holes are just really, really massive stars. And so if you have two stars, they may orbit with one, far to the outside of the other one. The other one might just be standing in place like spinning, whereas the other one is going way out and coming back in. And so we're going to calculate for these two, we'll say they're black holes because they're masses. Remember, the mass has to be at least 3. This is solar masses. That's that little thing right there. That's a unit. Remember, I said that if it's more than 2.5 solar masses, it's a black hole. So what does that tell you about these? One's 5 and one's 10. So these are probably black holes that we're looking at here. I have two of them. There's M1 and there's M2, and they're 2 light years apart. So our binary star system has x2, which is the distance between them, as 2 light years. And we want to find the center of mass that they're both rotating about. So one may be having a smaller little spin, and one may be kind of orbiting around the outside. I'll try and link to a video that shows this. I know there's videos that are simulations that NASA has worked on that really shows what happens when one is more massive than the other. And that'll give you a better kind of concept of how this works. All right, so here's our variables. We've got M1, and I know this is for 6th through 12th grade, and some of you may not have gone through variables yet. That's okay. If you just want to follow along, that's okay too. Our first mass is 10 solar masses. Our second mass is 5 solar masses. And here's the equation to find out how far from M1 our center of mass location is. So we take M2, the second mass, times the distance between them, x2, I'm going to get a little pointer here, times the distance between them, x2, and then we're dividing that by M1 plus M2, so the two masses added together. So let's go ahead and set up our equation here with the numbers. Remember, these are our variables. So I'm going to put those into that equation that we just saw. M2 is 5 solar masses. So put 5 there. X2, the distance between the two, is 2 light years. So I put a 2 there. They're multiplied together. And then on the bottom, we've got M1, so the mass of the first object. Oh, that's 10 solar masses. And then we've got M2, which is the mass of the second one, which is 5 solar masses. So we're going to go ahead and solve this. We have on the top 5 times 2, which is 10, so we put a 10 on top. Then we have 10 plus 5, which is 15. So let's go ahead and simplify this. You can plug this into, your calculator and just get a decimal, which is fine. But if you wanted to simplify it into its simplest form as a fraction, you would find the common denominator, the common, guys, it's been a while. The number that you can take out of both, it's 5. So yeah, 5 times 2 is 10, and 5 times 3 is 15. So you can take a 5 out of both the top and the bottom, and you end up with 2/3 light years. So this is going to be a distance, remember, because we're finding the distance from M1. So it's going to be 2/3 the distance light years. Or, sorry, it's a little dark here. Or if you went ahead and put it into a decimal form, it's 0.66 light years. So what does that look like if we put it back on our chart that we had? What does it look like in our binary star system? You've got M1, the more massive star or black hole. You've got M2, the less massive black hole. Here's approximately halfway. If they were equal mass, then the center of mass would be right in the middle. But it's not. So I kind of counted over a little bit. I said that, well, this is about 1/3, and this is about 2/3. So I put a dot there, and that is your center of mass. So they will both rotate with this center of mass being in the middle. So imagine I've got a little stick here, and I've got 2 little spinny balls on a stick that are rotating about the stick, and I flick it and it spins. It'll spin about this axis. And this is true for any binary star system. So if you want, you can adjust the masses. What happens if the masses are equal? What happens if you have smaller masses? Try it out. Okay, so that's our binary star system. Next, let's try one where we're bending light around a black hole. So remember I said that light bends when it encounters kind of the edge of that gravity well. It'll bend around the star, and you can see things that are actually behind the black hole or the massive object that you wouldn't normally see otherwise because the massive object is in the way. So here's us, our eyeballs. We're looking at something, and it appears, if we were looking straight at it, it looks like this object is right here in front of us. But we know, for some reason, we know that there is a black hole that is in between us and where the object appears to be. So in actuality, the object is sending, has light, a light wave, and the light wave is bending and then reaching our eyes. So the object isn't actually here. It's actually down here. And the light, that information that we have about the star, is bending and reaching our eyes around a black hole. So how do we know where the actual location of the star is in this case? We say that the angle that we're measuring is here, and we're going to say that that's a 30-degree bend. It's bending so that this angle right here is 30 degrees. And then we say that it looks like the star is 70 light years away, right there. So what is the actual distance between the apparent star location and the real star location? Let's find out. We're going to use trigonometry. So I've got my 30 degrees, got my 70 light years, and we're looking for D. If I'm using trigonometry, I like to use the SOHCAHTOA rule. Sine opposite hypotenuse, cosine adjacent side hypotenuse, and tangent opposite side adjacent side. So which one of these would we use here? Well, we know the adjacent, this is the angle we're using. So the side that's adjacent to that angle, we know the value of. And we want to know the side that's opposite of this angle. We want to know the distance there. So what has both the adjacent and the opposite? Well, that would be using tangent. So we would put it into this equation here. Tangent of our angle, 30 degrees, is opposite over adjacent. If I don't knock over my whole setup here. Alright, so we got opposite, that's D, that's opposite. Adjacent, that's 70, that's adjacent. And we're going to plug that into our equation. And then we want to isolate this variable. We're going to get this by itself on this side. So when we take things to the other side of the equation, when we cross the equal sign, we have to take it from division into multiplication. So here we're dividing by 70. We're going to flip it to the other side. We're going to multiply by 70. So go ahead and get your calculator out, and you'll do 70, or the computer. Wolfram Alpha is a magical experience. If you have not experienced wolframalpha.com, you can type in equations. So you get 70 times the tangent of your angle equals D. You type that in to your calculator or Wolfram Alpha or whatever you're using. You get 40.41 light years. So when we look at, when we look at this, you can see that the distance between the stars would be 40.41 light years. And that's quite a bit. So you're seeing a star that perhaps you wouldn't normally see in that position. Alright, so like I said, I'm going to try and post some links in the video when it replays. We'll have the one for the binary star system and showing you how they orbit each other. I'll probably have something in there that about gravitational waves. I found this really cool website for kids about gravitational waves and like explaining what those are. It's got videos. Yeah, so let me know how that goes. Try the experiment with the t-shirt and all that if you would like to do that. And I will see you guys next time. Please make recommendations for what kinds of topics you would like to see next. And I'll see you in the future. Bye.